In this podcast, we're going to delve a little bit deeper into looking at histograms and what they can tell us about the distribution of our data. We need to know about the distribution of our data so that we can make good choices about the kinds of statistical tasks that we're going to perform. So here we have the CycBike data set, which looks at a cyclist's distance from the curb, whether or not they were wearing a helmet, the passing distance of cars and the vehicles that passed them, and the time of day that they travelled. So the first thing I'm going to do is look again at this simple histogram, which we can use from the graphing function, and explore the distribution for the two main variables, which is distance from curb and also passing distance. So let's explore. So with cars, you can see that it's sort of much of a muchness. Most people are adhering to the central area here, where a few people are giving much more distance to the cyclist as they pass, and some people are being quite inconsiderate and driving quite closely. And that is more or less a normal distribution. There's some clustering, but it's still falling within the normal curve. With the cyclists, however, the data is not normally distributed. It's much more boxy in nature, with most cyclists doing more or less the same thing. And that, of course, is because they don't really have the same kind of range that a car driver has. There's an average point where most cyclists would drive, and the way that they would drive against the curb is going to be quite predictable. So therefore, you won't get the same normality in range. But what I'm also interested in is the behaviour of individuals who are driving different vehicles. And you can see here that we've got cars, LGVs, SUVs, buses, heavy goods, taxis, and PTW, which is motorbikes. So what we want to explore is the differences between those different vehicle drivers, and how we can do that is by telling SPSS that we want to look at each of these as individuals. So we use the data split file function, and what it will do is it will automatically allow you to compare groups across your variables. So we're going to compare by vehicle type. Now we're going to run the same type of histogram analysis this time, but we'll get lots of histograms, one for each of these different data sets. So what we want to do is passing distance. We've already split the file by vehicle type. And we want the normal curve. And now you will see that we've got several different histograms for each of the data sets, and we can start to see if any of these are violating the assumptions of normality. If we look at the first one, cars. Now you can see that there's many more cars in this sample than there are other types of vehicle, and that's of course because they're the greatest number of vehicles on the road. There's 1,708 cars. Most of them are adhering to the normal distribution. There's some peaking above it because of the volume, but by and large that's quite a normal distribution. Then we look at the LGVs. Again, there's some assumptions of normality violated. There's few that have gone very, very close. And most seem to be clustering around the middle range. So there's some violations, but it's not very serious. But when we get to the SUVs, we can see that actually there's some shift in behaviour. SUVs seem to be content to drive much closer, indeed, to motorists, and the average point for SUVs is about 1.2, whereas if you look at some of these here, it's a little bit higher. The midpoint is higher. So you can see more people are driving closer to the vehicles. Buses, however, seem to be much more considerate. Buses do not pass close, and more buses are more likely to be operating at the far end. Heavy goods drivers, however, are the majority of which are driving very close indeed to cyclists, with much fewer individuals giving more room to the cyclist. Taxis, again, a little bit more considerate, but not necessarily terribly normally distributed. And motorcyclists are more or less doing the same thing for a large part of this. Very few passing close, more individuals heading towards the midpoint. So when we're talking about our data under these circumstances, we're looking at the normal distribution and the extent to which the data moves to the right or to the left. And what we have are three different descriptions. And whenever some data is moving towards the left, it's called a positive skew. And when it's moving towards the right, it's called a negative skew. And you can see that the tails of the data change in both circumstances. When the data is skewed in this respect, it's not possible to look at it statistically using the mean, because the mean will not be a very reliable measure of central tendency. Instead, it's best to do something like the median, which is obtained through the scores that the majority of the participants presented. One of the problems with using histograms is the space that they require within publications, and reporting conventions mean that histograms go into an appendices in a report. You cannot give over the space in the main body of the results section. So what we can do is we can use numbers to spot normality. And we can do this through the analyze frequencies function. Bearing in mind that this data set is still split, so SPSS will still want to divide out each of the sets of data by vehicle type, and if you want to look at the entire data set, you need to flick it back to analyze all cases. But for now, we're going to look at it by vehicle type. So analyze descriptives frequencies, then we're looking at passing distance. What we don't want is display frequency tables, because what it will do, it will give us very long tables of each individual case, which is not required. What we want is the statistics. We want the mean, the median, and the skew, and the kurtosis. So the skew is how left or right the data set is in terms of a positive or a negative skew, and the kurtosis is how pointy it is, how far up. We also want the standard deviation. And then we click continue, and we should get a table which we can start to make some sense of. And you can see it's broken down each of the variables. It's given the mean, the median, the standard deviation, the skew and the standard error of skew, the kurtosis and the standard error of kurtosis. So these figures represent a pile-up of data at one end or the other. So here you can see that there is a pile up towards the top end of cars, which we know from looking at the distribution, because most people were doing less the same thing. And we've got another pile up again with the skewness of the LGVs. And if we go down to the bottom and look at the HGVs, we can see large numbers appearing again with no evidence of kurtosis. The further that these values are away from zero, the more likely there is to be some sort of violation of normal distribution. So we can see that most of this data is not falling clearly into normally distributed data formation. A further analysis that we can run is to look at the probability plots, the extent to which the data would fall onto a normal distribution. And what we can see here, if we look down this data set, is that here's the hypothesized line and here's our actual data. And you can see with cars, it's quite close to the line. There are very few deviations from normality, and therefore we can accept that this data set is not violating normal assumptions. LGV drivers, again, very close to the line, so strong probability that this data is passing normal assumptions. And the SUV drivers, you can see that there are starting to become some more deviations. This snake-like pattern suggests that there is a problem. Buses are not normally distributed. We know from when we looked at our original histogram, bus drivers were more likely to give more distance. Therefore, they would not be normally distributed. HGV drivers, the snake-like pattern again suggesting deviations from normality. Taxi drivers again, deviations from normality. Motorbike drivers, deviations from normality. So sometimes that can be an extra check to help you make sense of the underlying principles of your data. But again, these plots are not something that you put into the results section of your reports. They can go into an appendix and they can be alluded to within the write-up. Data is not normally distributed, therefore we need to use a non-parametric statistical test. And what we want to look at in this instance is the type of car against the passing distance. First of all, what we've got to do is we've got to ask SPSS to unsplit our file and reset it so that it doesn't compare groups in such an individual way, because what we want it to do is use that variable in a statistical analysis where this statistical analysis will make the comparisons for us. So we're going to look at if there are statistical differences between cars and the passing distances that they use from cyclists. So if this was normally distributed, we'd be running the one-way ANOVA, which is the parametric test, but we need a non-parametric test for independent samples, k independent samples, because we're not more than 2. And they're independent samples because a car is independent from a motorbike, is independent from a bus, etc. So we put a bus as the grouping variable vehicle type, and we know that we've got 7 different groups. And then we put passing distance, and this will carry out the Kruskal-Wallis test for us. We click OK. It's telling us that there is a statistically significant effect.